So in this video about the physical layer, I'm going to talk about two things. First, capacity, that is, how do we determine how many bits per second a given physical layer can support? And then modulation, how is it that you represent these bits on the medium itself? So it turns out that there's a theoretical limit on how much information a given channel can carry. Where in this case, a channel means a medium in which you're putting your information. This channel could be, say, a wire or wireless. It could be sound waves, whatever you want. It's just a term that's used to talk about the way in which the information is being communicated. And so this limit is called the Shannon limit, after Claude Shannon, who established it. And so it turns out that if you look at a given communication channel, and under a certain set of assumptions, which often hold pretty well, there's a very good approximation. It gives you a good sense as to what's possible. The channel capacity, or the number of bits per second you can send over a given channel, is B base 2 log 1 plus the signal-to-noise ratio, where B is the bandwidth of your communication. That is, what's the range of frequencies you can use. This is assuming that we're doing things with basically sinusoidal waves, etc. S is the signal strength, so how strong is the signal when it arrives at the receiver. And N is the noise. So any receiver is going to have some kind of noise, in the same way that when you're listening, you might think you hear silence, but there are sounds that are too faint for you to hear. It's because those sounds are below essentially the noise sensitivity of your ears. Or in the same way, if there's a white noise generator in the room, it can make it harder to hear things because there's this noise. And so all communication devices have noise. Often it's just due to thermal properties of the hardware. They're just stray electrons from thermal effects. And so that introduces some noise into the system. It's a big thing when you're engineering them. How do you bring the noise down? And so the basic point here is that the amount that we can send is proportional to the amount of bandwidth we have, like how large a chunk of frequencies can we use, and then the signal-to-noise ratio. Now, if we want a higher signal-to-noise ratio, it's just the signal divided by the noise. It requires either you have lower noise, that can be really expensive. It's harder to make hardware with lower noise, or a stronger signal. It requires that the signal be louder. This is, for example, why when you have more bars on your phone, it goes faster, because the signal-to-noise ratio of the data is faster because the signal-to-noise ratio is higher. It turns out that building hardware for very high bandwidth, so signals that have a tremendous bandwidth, is actually really hard. All these complications come into play. So it's not like you can just easily build a communication system with arbitrary channel capacity. There are all these engineering things which come into play, which is why we don't suddenly see terabit Ethernet. But so fundamentally, when we're talking about the capacity of a channel, I was talking about bandwidth and signal to noise. The way to think about this is, and this is how we generally represent signals, is in terms of analog signals. So think sinusoids. And so when we're talking about sinusoidal waves, here's a simple one here. There are a couple properties we care about that I'm going to talk about in the rest of this and some future videos. The first is the amplitude of the wave. So this is so the amplitude denotes the actual, one way to think of it is that how loud it is, the signal strength, loudness, signal strength. Second property is the wavelength. So how long is one of these waves? So the speed of light is approximately, so c, in vacuum, etc., is approximately 1 foot per nanosecond. That's a good rough rule of thumb. And so 1 billion feet per second. And so if, for example, I'm sending a signal whose wavelength is 1 foot, this would mean that it has a wavelength of 1 foot. Since the wave is traveling 1 billion feet per second, this means that there must be 1 billion waves per second. It's because this wave is traveling at 1 billion feet per second, the wavelength is 1 foot, I must have 1 billion waves per second. So this gives me the frequency. So how many waves do I expect a second? So 1 billion per second turns out to be 1 gigahertz. So 1 gigahertz wave this is electromagnetics, this is light, just at lower frequencies. A 1 gigahertz signal has a wavelength of about a foot. So Wi-Fi today, for example, operates at 2.4 gigahertz or around 5 gigahertz. So these have wavelengths of approximately 5 inches and 2.4 inches. Great. So here I'm talking about the frequency, the wavelength of a given wave, the amplitude of a given wave. But it turns out that when we send signals, we don't use a single frequency. We actually use a range of frequencies. So the bandwidth is the size of the frequency ranges that we use. For example, if you look at one Wi-Fi standard 802.11b, it's an older one. I'm just going to use that as a common example because it's one of the simpler ones since it's older. In 802.11b, if those of you who have used it, you have to select a channel. So channels 1 through 11. And often people use 1, 6, and 11. Each of these channels is 20 megahertz wide. And so when you look at a frequency map for 802.11b, you can see that all these channels, here's 1 and here's 11, and they take up about 20 megahertz of the frequency range, like so. And so you actually use a range of frequencies, and I'll show you sort of why this happens and how this happens. So finally, there's what we call phase. And so this is actually the timing of the waves within a wavelength. So here's a wave which is at this particular phase where the peak is occurring here. So let's call this T0. It's of course possible to send this exact same wave, but at a different phase. For example, we could send it like this. It's the same wave, but its phase is offset by 1/2 of the wavelength, and therefore 180 degrees. And so it turns out that things we do to control, as we'll see in a second, that we do to control waves, and that we do to send signals involve changing the amplitude of waves, changing the frequency of waves, as well as changing the phase of these waves. But fundamentally, these waves are what's going on underneath in the system. So given that we're using waves, there's a whole bunch of ways we can represent bits. This is one of the simplest ways, is something called amplitude shift keying, or ASK. And what this process is called modulation. How do I take a signal, or take a particular piece of data, and then modulate my waves to represent that signal? So here, to represent that data. How do I modulate the signal to represent the data? So here, for example, I have an amplitude shift keying where 1 has a small amplitude, 0 has a small amplitude, and 1 has a larger amplitude. So I want to send a 0, I send this smaller wave, and when I want to send a 1, I send this larger wave. Another approach that you can use is something called frequency shift keying, where you use 2 separate frequencies. And so here's a 1, and here's a 0. The 0 happens to be the higher frequency, the 1 is the lower frequency. And then as I want to send out a stream of 0s and 1s, I just move these frequencies back and forth. Oh, I'm sending 1, 1, 1, so I use longer, 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 then 0, 0, 0, 0, shorter, 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 shorter. The other side can decode these and then figure out what bits are being sent. So amplitude shift keying turns out to be it's very commonly used, especially in wired networks. And the reason is that when you have a wire, your medium is controlled. The signal you put on one side, it decreases a little bit on the other side, but not by very much. Wires do not have a lot of resistance. That's why we use them to carry power. And so amplitude shift keying is commonly used in wired systems just because it's very simple and it works great. So most common wired Ethernet today uses amplitude shift keying. For example, 100 base T and 1000 base T, this is 100 megabit and gigabit Ethernet, use what's called PAM5, which means 5 levels of amplitude modulation. They're called pulses because you're sending these pulses at these different amplitudes. So think of these basically as voltages, -2, -1, 0, +1, +2. And so you're sending these different voltages along the wire. Turns out 10G base T or 10 gigabit Ethernet, one of the sort of upcoming standards people are adopting, needs to use more levels of amplitudes in order to get all of its data through. And so it uses PAM16, so 16 levels rather than 5. So another form of modulation that's really popular is what's called phase shift keying. So unlike amplitude shift keying, we're adjusting the amplitude of the waves, or frequency shift keying, we're using different frequencies. With phase shift keying, you adjust the phase of the waves. So here, for example, let's say 0, this is a phase of 0 degrees. But then to send a 1, as you can see, my phase is reversed. This is a phase of 180 degrees, right, or minus 180 degrees. The two are the same. And then here to send to 0 again, I start sending at a phase of 0 degrees again. So phase shift keying is really useful when your channel, when your medium is such that you can have significant variations in signal strength. So amplitude shift keying, you need to be able to figure out what all the different amplitudes are. So when the actual attenuation or the signal strength is stable, like in a wire, that's great. But for example, in wireless situations, amplitude is a bit harder. Phase is can be easier. So situations where phase shift keying is used are in, say, a DSL, digital subscriber lines, that are along long phone lines where there could be weather and wires shaking and bad connections, but really long wires. Cable modems, right, that are stretching out through an entire neighborhood. Wireless systems, these all use phase shift keying. Some of them also use amplitude, but they, unlike wired Ethernet, all these systems use phase. And so one kind of phase shift keying is binary phase shift keying, or BPSK. And so you basically have two phases, 0 degrees, and pi, or 180 degrees. And so, like in that prior picture, you're either sending something at this phase, let's say that's 0, or you're sending it at this phase, which is, say, 180 degrees. So this is 180 degrees, pi. So this is 0, 0. So for example, BPSK is used in 802.11b, an older Wi-Fi standard, at low speeds, 1 megabit and 2 megabit per second. There's also a quadrature phase shift keying, QPSK, where now we have 4 phases. As you can imagine, just as we have 0 and 180 degrees, with QPSK, we have 0, 90 degrees, 180 degrees, 270, or 0, pi over 2, pi, 3 pi over 2, radians and degrees respectively. So it turns out QPSK is also used in this older Wi-Fi standard 802.11b. It's used at the higher speeds, 5.5 megabits per second and 11 megabits per second. Now, one thing that should come out from this is that the reason why we might use QPSK versus BPSK or PAM16 rather than PAM5 is that for a given signal we're sending, we can send more information. So for example, BPSK, each wave we send carries 1 bit of information. Is it 0 or pi? In contrast, for QPSK, each symbol that we send on the waves, each little chunk of data we're sending at the physical layer, contains 2 bits. Is it 0, pi over 2, pi, or 3 pi over 2? You could say represent those as 0, 0, 0, 1, 1, 0, 1, 1. That's not actually how it's done, but the idea is you can actually, by having these denser representations, you're sending more information per unit time. Now, one reason why phase shift keying is very popular is it actually turns out it's very easy to shift phase. So for example, here, if I just have a carrier wave at, say, 0 degrees, and another carrier wave, at minus 90 degrees, then any linear combination of these two allows me to create any intermediate frequency. So for example, here, if I combine 0 degrees with minus 90 degrees, just add these two waves up, I'll get something at minus 45 degrees. That's if it's a, sort of 1-to-1 equality. If, for example, instead I did 0.51, then we'd have something a little closer to the 0 degrees, right? Assuming that this is the minus 90 degrees and this is the 0 degrees. Right? Similarly, if I did, rather than 1, 1, if I did minus 1, 1, so this is minus 90 degrees, this is 0 degrees, then what we'd see is, rather than a wave between these two, the wave would be here, right? It would be at plus 45 degrees with this setting. And so just with these two things, you can combine and create any intermediate frequency you want, which turns out to be really useful in hardware. And in fact, that's exactly how hardware does it, using something called IQ modulation. So I means the in-phase component, so at 0 degrees, Q is the quadrature component at minus 90 degrees. This is just a complex way of saying, hey, if we want to create any phase between 0 and, say 300, 0 and basically minus 0 wrapping around, we can just combine these two I and Q with some linear factor and get that. So for example, let's look at those two things we had of BPSK and QPSK. So BPSK has two phases, 0 and 180 degrees. What are the IQ values of those? Well, so for 0 degrees, it's going to be 1, 0, right? We want fully at 0 degrees. For 180 degrees, well, that's the opposite of 0, right? It's, if you were to think about it, on the unit circle, say, here's 0, here's 180 degrees. So just as here we had +1, here we're going to have -1. So -1, comma 0. For QPSK, we're going to have 4 phases. Let's say 0, 270, 180, and 90. So again, 0 is going to be 1, comma 0. But now 270, right? 270 is down here, right? So here's -90 / 270. Right? So 270 is going to be 0, comma 1. 180 is going to be just like in BPSK, -1, comma 0. And 90 is going to be 0, comma -1. And so we can, just by changing the scaling factors of the I and the Q, create any phase we want of a signal. And that's exactly kind of what it looks like in hardware, is that we have these IQ values coming in, these digital values, then we have these 2 carrier frequencies, and we end up adding them up to come out on the RF. This is then what comes out of the antenna. This is actually how you build the hardware with these IQ values. But what's really valuable, and the reason why I'm going into them about IQ constellations, is that they actually lend themselves to a really, really simple and easy to understand graphical representation of what's going on down at the physical layer. And so the way I think of it is, if we take these IQ values and we just represent them on a 2D grid, right, we can use what's called an IQ constellation, this 2D plot. In this case, in these 2D plots, the angle of your vector represents the phase of the signal, right? Like here, say we have 45 degrees, right? Here we have 135 degrees. And then the length of this vector represents the amplitude of the signal. So if we look at something like on-off keying, where you either send something or it's silent, we see here's an amplitude of 1, amplitude of 0. There's more on-off keying, right? There's no change in the phase. Amplitude shift keying, where we have 2 different amplitudes to use. See, here's a 1 and here's a 0. We're just changing the amplitudes. We're not actually changing the phase, we're just changing the value of I. BPSK, remember there are 2 phases, 0 and 180, and so that's what we see here. So here is 180 to say represent the 1, and here is 0, say to represent the 0. QPSK also has 4 points with these 4 different phases. I also could have rotated them and say drawn them like this, but it's still easier to see them when there are these 4 corners like this. This is a way to just represent what the wireless signal is. It's this nice pictorial representation. When we start talking about signal and noise and those ratios, things will start to make a little more sense. It'll be a really clear depiction of what's happening. And so just recall, we can represent any intermediate phase from this 0 and -90. There's just some linear combination of those 2. Now at some point at the link layer, we have bits. Bits are coming in. We have some packet from the network layer, and we have some frame at the link layer with some bits in it, 0, 1, 1, 0, 0, 1, 1, organized into bytes, into octets, however. But down at the physical layer, we can't necessarily transmit a whole byte. It might be that we can only transmit a couple bits at a time. And so in the physical layer, we talk about symbols. And the symbol is the unit of transfer that the physical layer can provide. So often when we talk about things at the link layer, we talk about, oh, we add a byte, but that might not be the boundary down at the physical layer. And the reason is, as I talked about before, a symbol can contain more than 1 bit. So BPSK has 1 bit per symbol. There's 2 phases. QPSK has 4 phases, has 2 bits per symbol. But then you also get situations like PAM5 that's used in 100 megabit and 1 gigabit Ethernet on a Cat5 cable, where there's these 5 voltage levels. There are 5 different symbols that you can use. And that doesn't necessarily even map perfectly to a number of bits, right? 5 symbols is just over 2 bits. That's important to realize that although up at the link layer, even passed down to the physical area of a sequence of bits, there's this transformation that occurs, turning that sequence of bits into a sequence of symbols down at the physical layer. So finally, I've talked about amplitude keying, I've talked about phase keying. There's this approach you use today. It's very, very common. You see it in almost all modern communication systems called QAM, which really stands for quadrature amplitude modulation. Or basically this means phase and amplitude keying at the same time. And so, whereas ASK, amplitude shift keying, uses only the amplitude, and phase shift keying uses only the phase, in QAM, we use both. So to give you an example, the way this is usually talked about, say 16 QAM means that we have 16 different symbols. And so we can represent, for each symbol, we can represent 4 bits. 256 QAM means there's 256 different symbols. It means we can represent, for each symbol, we can represent 8 bits. And so returning to the IQ plot, or the modulation plot, here's what 16 QAM looks like. So this is the constellation, the IQ constellation used in HSPDA, which is a 3G data standard. And so, as you can see, there are these values from 3, to -3, -3, and they map to different bits. And so here I've shown in gray the I and Q values, right? So here's an I of 3, a Q of 1, I of 3, Q of 3, I of -1, Q of 3, Q of 1, sorry. And then what the represented bits are above the physical layer. And so here's an example IQ constellation for 16 QAM. And as we can see, it's adjusting not only the amplitude, that is the length of the vector coming out of the origin, but also the phase, which is the orientation of the vector coming out of the origin. So here's an example IQ constellation used in modern 3G systems, 16 QAM, 16 different symbols, and here's how bits map to these symbols. So for example, if I wanted to send 1011, 1001, I would send 1011. So I'd send this first. Right? This would be the first symbol that I send, number 1. Then 1001, I would send this symbol, second. And so if we're to go down and dig into and see what's happening down in the physical layer, we're going to see a signal transmitted with a phase of what's essentially 135 degrees, right? This is 135 degrees. And an amplitude, let's say, of x. Then the next symbol is going to be with this angle, right, with this phase, which is approximately, let's say, 105 degrees, and a slightly smaller amplitude, right, because this vector is longer. And so that's what you actually see in terms of the waves in the physical layer. So what's used today? Well, AS amplitude shift keying is basically all of wired Ethernet uses amplitude shift keying. It's very rare for communication systems to use frequency shift keying. There are some examples like the National Weather Service's Weather Radio, and Bluetooth actually uses it in some forms. Binary phase shift keying is used basically by all of the Wi-Fi standards, ABGN. It's also used in WiMAX. Quadrature phase shift keying is used in Wi-Fi. There's low power wireless like Zigbee called 802.15.4. 3G, LTE, WiMAX. 16 QAM is used in Wi-Fi, as well as these data standards for cellular phones, for mobile phones, mobile telephony. 64 QAM is used in Wi-Fi as well as LTE and WiMAX. And so you can see that there are the older, the more modern standards are the ones that are using the denser constellations. People have made things go faster and faster. So just an overview. There are many different ways that you can take your bits and then represent them in terms of a physical medium, convert them into voltages, phases, frequencies, etc. Wired Ethernet and wired systems often use amplitude to represent signals, whereas most technologies today, like wireless technologies or things that are over less controlled media, like cable modems, DSL, use phase shift keying or a combination of phase and amplitude called QAM, quadrature amplitude modulation. And one of the key things is that you can represent a QAM symbol, or in fact any of these, as a linear combination of two things. The in-phase component I at 0 degrees and the quadrature component Q at -90 degrees. This is actually how circuits do it today. And what's really nice is that it gives you a very good pictorial representation of what the signal looks like and how it's controlled and how it's modulated and how those map to bits.